f of t is equal to sine a t. Okay, so here we'll say the Laplace transform of f of t, where our f of t is sine t. That means you say the Laplace transform of sine a t. Now, going with the definition of Laplace transform, we say that Laplace transform of f of t is given by the integral from 0 to infinity e raised to the power of minus st f of t dt. Okay, here we have our function f of t to be sine a t. So when we say Laplace transform of sine a t is going to be the integral from 0 to infinity e raised to the power of minus st sine a t dt. Okay, so now evaluating this integral, we can use any method, but in this video I'm going to show you how to use two methods. Okay, I'm going to show you two methods you can use. Now, the first method is called using Euler's method. Okay, using Euler's method. And number two is using the first principle method, or using the first principle. Now let's go with the first one, Euler's formula. You know, in complex number, Euler's formula, when you have e raised to the power of ix, you know, is given by cos x plus I sine x. Is that true? Yes. Now, what if you have e raised to the power of minus ix? That means in place of x, you replace it with minus x. Is that true? In place of x, you replace with minus x. So that means we're going to have cos minus x plus I sine minus x. So this cos will swallow this negative sign. That means it's going to give us cos x. And then in sine minus x, the negative will come outside. We have minus I sine x. All right, good. Now let's call this equation 2. And then the first one, we have e raised to the power of ix, which is equal to cos x plus I sine x. Let's call it equation 1. Okay, look at these two equations very well. When you say equation 1 plus equation 2, what are you going to have? That means you say e raised to the power of ix plus e raised to the power of minus ix is equal to, you know, this place we have in equation 1 and 2, we have, in the first one we have plus I sine x, and in the second one we have minus I sine x. So when you add these two terms together, it will give you 0. So here we have cos x plus cos x. It's going to give us 2 cos x. All right, good. We can try to make cos x the subject. So in doing so, we're going to have cos x is equal to e raised to power ix plus e raised to power minus ix all over 2. All right, all over 2. Again, in this equation 1 and 2, we can say equation 1 minus equation 2. Okay, we can say equation 1 minus equation 2. In doing so, what are we going to have? We're going to say e raised to the power of ix minus e raised to the power of minus ix is going to give us 2I sine x, because when you say cos x minus cos x, it's going to give you 0. And then when you say I sine x minus minus I sine x, minus minus will give you positive. So we have 2I sine x. Okay, good. Let's also try to make this sine x the subject. So in doing so, that means we divide both sides by 2I. So if we divide both sides by 2I, we're going to have sine x is equal to e raised to the power of ix minus e raised to the power of minus ix all over 2I. Okay, yes, in this place where we say equation 1 plus equation 2 and equation 1 minus equation 2, look at what we have. We say that cos x is equal to e raised to the power of ix plus e raised to the power minus ix all over 2. And then sin x is giving us e raised to the power of ix minus e raised to the power of minus ix all over 2I. All right, good. But then you see that in the function we have, we are given f of t is equal to sine at. But what we have here is sine x. So in place of x, we can replace it with at. In place of x, we can write at. Okay? Now, in this place, that means we're going to have e raised to power of iat. Hello? iat. We have e raised to power of ix. So in place of x, we replace it with at. So we have e raised to the power of iat minus e raised to the power of minus iat all over 2I. All right, good. So here we have f of t, the function f of t is equal to sine at. Then we take the Laplace of both sides. We say the Laplace of f of t is equal to the Laplace transform of sine at. Going by definition of Laplace of f of t, we say that Laplace transform of f of t is given by the integral from 0 to infinity e raised to the power of minus st f of t dt. Okay, so now we say the Laplace transform of sine at. In place of f of t, we replace it with f of t. In place of f of t, we write sine at. That means we are going to have the Laplace transform of sine at is equal to the integral from 0 to infinity e raised to the power of minus st sine at dt. Okay, good. And then we just discovered that sine at has a new value, which is e raised to the power of iat minus e raised to the power of minus iat all over 2I. So in place of this sine at, we can write this e raised to the power of iat minus e raised to the power of minus iat all over 2I. Okay, so in doing so, this is what we are going to have. We have the integral from 0 to infinity e raised to the power of minus st open bracket e raised to the power of iat minus e raised to the power of minus iat all over 2I. Okay, we have dt. Now let's go. In this place, in this bracket, where we have all over 2I, we can factor out 1 all over 2I. Okay, and then we'll see that it is a constant. So when we factor out this 1 all over 2I, we take it behind the integral sign. So taking it behind the integral sign, we have 1 all over 2I, the integral of e raised to the power of minus st open bracket e raised to the power of iat minus e raised to the power of minus iat all the bracket dt. Okay, good. Here, let's open this bracket. Let's open this bracket. For us to open this bracket, we use this e raised to the power of minus st to multiply the content inside the bracket. So in doing so, we're going to have 1 all over 2I, the integral from 0 to infinity e raised to the power of minus st multiplied by e raised to the power of iat, okay, minus we have e raised to the power of minus st multiplied by e raised to the power of minus iat dt. That is when you use e raised to the power of minus st to open the bracket. Okay, good. Now, following the law of indices, since the base e are the same, we simply add their power. Okay, so that means we are going to have e raised to the power of minus st plus iat minus e raised to the power of minus st minus iat dt. Okay, good. Now let's factor out t, because t is common in both the exponents. Now in factoring out t, we have e raised to the power of minus s plus ia, close the bracket, t minus e, open bracket, minus s minus ia, close bracket, t dt. Okay, now let's apply this integral sign into the expression. So applying it inside, we are going to have 1 all over 2i, open bracket, the integral of e raised to the power of minus s plus ia, close bracket, t dt, minus the integral from 0 to infinity e raised to the power of, we factor out minus. Okay, we have minus open bracket s plus ia, close bracket, t. Okay, we have the t. Now from here we can integrate properly. Okay, so integrating properly, here is what we are going to have. We have 1 all over 2i, open bracket, e raised to the power of minus s plus ia, close bracket, t all over minus s plus ia, then interval from 0 to infinity, then minus open bracket e raised to the power of minus open bracket s plus ia, close bracket, t all over minus open bracket s plus ia, and then our limit from lower limit to upper limit, which is from 0 to infinity. Now let's go. In this first bracket, we can simply factor out 1 all over minus s plus ia. Okay, so as we do so, this is what we have remaining. We have e raised to the power of minus s plus ia, close bracket, t, and then our interval 0 to infinity, minus, we also factor out 1 all over minus open bracket x plus ia. So as we do so, we have e raised to the power of s plus ia, close bracket, t, and then our boundary we have from 0 to infinity. All right, good. Now in this case we can now go ahead and plug the limit, the upper limit minus the lower limit. So in doing so, we have 1 all over 2i, open bracket, 1 all over minus s plus ia, open bracket, e raised to the power of minus s plus ia, close the bracket, infinity, minus e raised to the power of minus s plus ia, close the bracket, 0, minus open bracket 1 all over minus open bracket s plus ia, close the bracket, e raised to the power of minus s plus ia, close bracket, infinity, minus e raised to the power of minus open bracket s plus ia, close bracket, 0. Okay, so in the inner bracket, where we have e raised to the power of minus s plus ia, infinity, so that is going to give us 0, and then the other one is going to give us 1. So here we have 0 minus 1, and then going to the next bracket is still going to give us the same thing, 0 minus 1. All right, good. So when we say 0 minus 1 is the same as minus 1, so minus 1 multiplied by the content inside the bracket, which is 1 all over minus s plus ia. So your multiply is going to give us positive 1 all over s minus ia. Then we have minus. In this side, we have 0 minus 1, which is minus 1. then multiply by 1 all over minus open bracket s plus ia. Okay, so here we're going to have 1 all over s minus ia minus 1 all over s plus ia. Okay, now let's combine these two items inside this bracket. Okay, so that means we're going to have 1 all over s minus ia minus 1 all over s plus ia. So combining these two items, we look for their LCM. The LCM is going to give you s minus I in bracket s plus I in bracket. Okay, so dividing and multiplying, we're going to have s plus ia minus s minus ia. Okay, now when you open the bracket, we're going to have s plus ia minus s plus ia all over. Multiplying the denominator, we have s squared plus ias minus ias minus I squared a squared. Okay, so in our numerator, s minus s will give you 0. And then we're going to be left with ia plus ia. It will give us 2ia. All over, in the denominator, we have x squared plus a squared. Recall that I squared is minus 1, okay? So minus 1 multiplied by minus a squared, it will give you positive a squared. So here we have 1 all over 2i in bracket 2ia all over s squared plus a squared. So 2i in the numerator, we cancel the 2i, the denominator outside. So we are going to be left with a all over s squared plus a squared. Okay, so here we see that f of t equal to sine at. The Laplace transform of this function sine at is giving us a all over s squared plus a squared, where a can assume any value. Now let's say, for instance, we have sine 3t. So here our a is 3. So when we say the Laplace transform of sine 3t is going to give us 3 all over s squared plus 9. Okay, when you say a squared, that is 3 times 3, it will give us 9. So the Laplace transform of sine 3t is going to give us 3 all over s squared plus 9. All right, good. Now let's go.